In this video, we're going to look at two-dimensional motion in a gravitational field, which is summed up in this box here. But we're actually going to see where all this comes from and derive these vectors. So let's start with the given information. Consider an object moving in a plane with a horizontal x-axis and a vertical y-axis, subject only to the force of gravity. Given the initial velocity, v of 0 is u sub 0, v sub 0, and the initial position, r of 0, given as x sub 0, y sub 0, the velocity of the object for t greater than or equal to 0 is given by the derivative of the position function, right? So here it's stated down here that the position function is given by x of t, y of t. So the velocity is the derivative of those. And it says that's going to come out to be u sub 0, comma, negative g times t plus v sub 0. We're going to show where that comes from. And that the position function can be found by this formula right here. I'm not going to read it all, okay? So what this is saying is if we know these initial conditions, if we are given the initial velocity, and if we're given the initial position, then we can determine the formula for the velocity. It's going to come out to be this. And we can determine the formula for the position vector. It's going to come out to be that by just plugging in the values of u sub 0, x sub 0, v sub 0, y sub 0. All right, so a couple things on this. G here is gravity. It says subject only to the force of gravity up here, but it's not necessarily given. We'll give it down here. Here it is right here. So gravity, that variable, it's not really a variable, but that letter there, g, we have these two values we can use depending on whether we're using meters or feet. And then this is only using gravity as the only force, okay, which is a little bit of a stretch, like we're taking out other forces that could be acting on this thing, like let's say air resistance, or even if there's a wind, but even just air resistance. We're taking that out of the equation here. So in Activity 5, we're going to explore where these formulas come from, all right, which I've titled Don't Drink and Derive, R of t and v of t. Have to make that joke at least once a quarter. All right, so Newton's second law of motion, which is used to model the motion of most objects, states that mass times acceleration equals the sum of all forces. And those of you guys that have dealt with physics before have probably seen this formula. So remember, acceleration is the second derivative of the position function. So we could throw that in there. And I'm just going to write that as the acceleration function right here. So again, remember, we're supposing that the only force acting on the object is gravity. So the gravitational force is given by this vector, capital F, which is 0, comma, negative m times g. Let me rewrite that because my PowerPoint put a little line break in there, which is kind of hard to read. So let's write it down here. So there's our force vector. And so again, this force vector is only the force that is subject to gravity, or the force of gravity, not any other forces, okay? The mass times the gravity. All right, so let's go down here and plug this in. So instead of the sum of all forces here, I'm going to plug in this vector that represents the sum of all forces, which is just gravity. Now, if I factor an m out of this vector on the right-hand side and divide both sides by m, I come up with a vector for my acceleration. And this is where we start the process of working backwards to find the velocity vector and the position vector. So we know that the acceleration vector is just given by 0 and the opposite of g. All right, so let's go and remind ourselves notationally, and this is up here in yellow, but I rewrote it down here, that the initial velocity of the object at t equals 0 is given by the vector u sub 0, v sub 0, and the initial position of the object is given by r sub 0 equals x sub 0, y sub 0. So now what we're going to do is we're going to find the velocity vector and the position vector by working backwards, right? You know what we're going to do? Can you feel it? Remember that if we have the derivative of the position vector, we get the velocity vector. if we have the derivative of the velocity vector or the second derivative of the position vector, we get the acceleration vector. So if I'm given the acceleration vector and I want to find the velocity vector, that's right, we're going to take the integral. We're going to do that antiderivative. So let's start there. A, solve for v of t. So the velocity vector is going to be the antiderivative of the acceleration vector, dt. All right, this looks like something we can do. So remember our acceleration vector up here in this scenario with only gravity as the only force here. We're going to take the integral of this vector valued function in terms of t. So the way we do that is just by integrating each component. All right, so the integral of 0 is going to be some constant. Oh, let's call it c sub 1. So we're going to have some other constants in here. Let's call it c sub 1 times t. Nope, not times t, just a constant. There we go. The next component, gravity, is a constant. And I take the antiderivative of that, and I'm going to have, whoa, not q, other direction, g of t. Now, like any other integral, this could be affected by a constant as well, a constant vector, some constant vector function that has two different components to it. So maybe we even want to write that out. Maybe we want to name these components so we really remind ourselves that this constant is a constant vector. I've already used c sub 1, so let's go c sub 2, c sub 3, some other constants. So now I could rewrite this as c1 plus c2 for my first component, and then opposite of gt plus c3 as my second component. Now, how do I figure out what these constants are? Well, that's where the initial value comes into play. We know that v sub 0 is equal to u sub 0, v sub 0. Okay, so let's take this guy here. This is my v of t. This is my v of t, right? So let's plug in v of 0. So I'm still going to have this constant here, but I'm going to put a 0 in for this t, right? We're putting 0 in for t, so that's going to go away. So that's going to give me just c sub 3. All right, well, what do we know about v evaluated at 0? Up here, we know that we've defined those to be these values, u sub 0, v sub 0. So u sub 0, v sub 0 equals these constants here. Okay, so c1 plus c2 equals u sub 0. So I'm going to go down here, and I'm going to substitute in u sub 0, which is the x-coordinate of my initial velocity. And then I have negative g times t, and what is c sub 3? C sub 3 is the y-coordinate of my initial velocity. So I'm going to substitute that in right here, plus v sub 0. So there we have our formula for the velocity function. Let's put that in a nice rectangle to make it official. Okay, let's go back up here and look at what we had in our box up here, right? They said to find the velocity function, this is what you have. So we just showed how you could derive that. So next thing we're going to do is we're going to derive this. And actually, this might be something that you want to do on your own. Maybe I'll set it up for you. I think this would be a good thing for you to do on your own. So I'm going to set it up, kind of get you started. And I want you to follow that same process and show that the position function is given by this formula here. So let's set that up. All right, so let's go down here. It's got enough room to get started. So B, we're going to solve for r of t. So since r of t, since the derivative of r of t is v of t, the velocity function, then to find r of t, I would need to do the antiderivative of v of t, dt. So we're going to do the antiderivative of the constant u sub 0 times negative gt plus v sub 0 dt. Okay, so you're going to do the same kind of thing we did up here. You're going to, take the integral, do the antiderivative, put the constants in there, and then you're going to use the fact that the initial position, let me scroll up a little bit, is given by x sub 0, y sub 0. The initial position is given by x sub 0, y sub 0. You're going to use that to solve for your constants and get rid of all your constants, whatever constants you end up with. Last time we had C1, C2, C3 to solve for the constants. So when you're done, you want those constants gone. You want everything in terms of x sub 0, y sub 0, u sub 0, v sub 0. You want it to come out to look like this. Okay, we have our g and our t in there, but the only constants we have are the u sub 0s, x sub 0. And why is that? Well, because those are things that we know. Those are things we're going to be given. We're going to be given the initial velocity, or we're going to be given the initial position. So we can take those values, those constants, and plug them into this formula and come up with our position function. All right, so go ahead and finish this problem and show that that works, and then we will move on to an example.